Welcome. Dear students, today we are going to see theory of orientation and reactivity in benzene ring. In part 1, that is in this part of the video, we will see what are orthopara directors and what are activating and deactivating substituents, or what are ring activators or ring deactivators. In the next part of the video, that is in part 2, we will see as to why electron donating group act as orthopara directors and ring activators, and why electron withdrawing group act as meta directors or ring deactivators. In this part, we will just focus our attention on what are orthopara directors and what are ring activators and ring deactivators. So without wasting much of the time, let us start the theory of orientation and reactivity of benzene ring. Let us assume what would be the situation. What would be the situation if an electrophile encounters benzene ring which is already having a primary substituent attached to it? I repeat the question. What would happen if an electrophile encounters a benzene ring which already has a primary substituent attached to it? What would happen? Whether it will attack? That is the first question. Yes, it will attack. Why? Because benzene ring has 6 pi electrons. It is rich in electron. An electrophile is not so rich. It's poor, of course. That's why it's having a positive charge over it. So it wants to become neutral. So it would attack. Where it would attack? So many positions are available here. 2, 3, 4, 5, 6. Mathematically speaking, or statistically saying, it can attack at any of these positions. Right? So if it attacks at 2 and 6 positions, we get 2 ortho products. If it attacks at 3 and 5 position, we get 2 meta products. If it attacks at the 4th position, we get 1 para product. Correct? There are equal probability. Equally, E can attack here, E can also attack here. That is equal probability. E can attack here, it can attack here. So more ortho and meta products can be formed. While there is only one position for para, so only one can be formed for para. How many total products are formed? See, look at this. 5 di-substituted products are formed. 5 di-substituted products are formed. Ortho how much? 2 out of 5. Out of 5, 2 are ortho. Meta, 2 out of 5. Out of 5, 2 are meta. And para, how much? 1 out of 5. So if you're taking the percentage, you can say 40% ortho product will be formed, 40% meta product will be formed, and 20% para product will be formed. So statistically speaking, if the electrophile it encounters a benzene ring to which a primary substituent is attached, then electrophile would have more probability to go to ortho position and meta position, and thereby the major products will be ortho product and meta product, while the minor product will be the para product, because there is only one probability, right? So that is statistically speaking or mathematically saying this, but experimentally it is not the case. Let us see how. Let us assume that S is OH group. Let us assume that S is OH group. So we took S, here phenol we took, and as electrophile we took NO2 plus. We know how NO2 plus comes. We use the nitrating mixture, conc HNO3 and conc H2SO4. If you heat it, you will get this electrophile NO2 plus. Now what is experimental result? Let us see. First I will draw the 3 isomers and then I will tell you the yields, that is the experimental result. So these are the 3 isomers. This is the ortho isomer, this is the para isomer, and this is the meta isomer. 3 products will be formed if NO2 plus attacks the phenol. S here is OH, that is primary substituent here is OH. This how much yield? That is the question. Orthoisomer as predicted statistically it is matching. 58% will be orthoisomer, 41% will be para-isomer and only 1% meta-isomer. So that is very astonishing because statistically meta-isomer should be equal to orthoisomer and para-isomer should have been minor product. So statistically it is very contradictory. This is very contradictory. Now leave that. I am taking primary substituent as COOH group. Okay. When I am treating it with benzoic acid where S is equal to COOH, then the result that I get is what I am going to write. We will discuss the yield. First let me write the three isomers that are formed. Para and there goes the meta. You know the yields here. Meta isomer is 85% meta isomer. Ortho isomer is 14.6% ortho isomer and para isomer is 0.4%. Meta isomer is formed as major product. We don't have any issue with that. But look at the ortho isomer. It should have been equal to meta isomer, something like 50-50%, and para isomer should have been the minor product. Here it is minor product, but look at the ortho isomer here, how much less is it formed, so much less that now it has become negligible. So what is the reason for this? It is not matching to what we have seen statistically. What has happened here? We will come to this question later, to the answer of this question later. Let me try out other things also here. If I am replacing OH, if I am taking it as OR, S as OR, I get the same kind of results where orthoisomer and para-isomer are the major products. I get the same kind of results if I am replacing it with OR. If I am replacing it with O minus, I get the same kind of results. If I am taking NH2 here, I am getting same kind of result. NHR, NR2, same kinds of results I am getting where ortho and para isomers are the major product. This category, let's come to this category. Same behavior is seen if I am taking aldehyde. Same behavior. Meta isomer will be formed as the major product. If I am taking ketone, I am seeing same output. Meta isomer, meta product will be the major product. So the major product is actually decided by what? That is the question. What decides which product will be major? What decides which product will be major? Has anything changed here? Is the benzene ring same for both? Yes, the benzene ring is same for the both. Is the electrophile same for the both? Yes, electrophile is also same for both. Then what is the only difference? The difference is in primary substituent, that is S. And as primary substituent changes, the major product that forms also changes. I hope I am clear. As the primary substituent, everything is same, else everything is same. Only difference is S. As S changes, as primary substituent changes, the major product, what will be formed as the major product, that also is changing. So we conducted a lot of experiments using different primary substituents. Okay, we conducted a lot of experiments using different primary substituents and we observed the major products that are formed, and accordingly we have seen that primary substituents can be divided into two classes. What are those two classes? Those two classes are ortho-para directors and the second class is meta-director. Primary substituents can be divided into two classes. ortho-para directors and meta-directors. If you are using ortho-para director, suppose this S is an ortho-para director, then electrophile, it will be directed towards ortho position and para position. So that will be formed as major products. Okay, this is through experimentation only we have found. Okay, by randomly taking different type of SS, by taking different type of primary substituents, and by observing the major products, we have subdivided the primary substituents into two classes. That which directs the incoming electrophile into ortho and para position, that primary substituents are called as ortho-para directors. And meta-directors are those primary substituents that direct the second electrophile towards the meta position. In this case, meta product will be the major product. In this case, ortho and para product will be major product. So I hope it is clear. Ortho-para directors are primary substituents that direct the incoming electrophile towards ortho and para position. We have seen so many examples, OH, OR, right? And meta-directors are those primary substituents that direct the incoming electrophile into meta position. Now, what are the conditions for ortho-para director? Ortho-para director, two conditions only. There are only two conditions for ortho-para director. Shall I say? Yes. Number one, the S group, that primary substituent, it should have negative charge. That is first condition. It should have a negative charge. If it is not having a negative charge, then it should have a lone pair of electron. Okay, that is the first condition, so that it can give the electrons to benzene ring. That is the prime purpose, so that it can donate the electron to benzene ring. If negative charge, it can donate. If there is lone pair, it can donate. So such kind of substituents are eligible for this category, ortho-para director. Meta-directors are those, what is the eligibility of S? It should fulfill two conditions. We will come to this later. First we will discuss about ortho-para directors. Okay. What are the two conditions that I have said? Either the primary substituent should have a negative charge, or it should have a lone pair of electron. Okay. So we have got lot of examples for this. Look at this. O minus. Look at the lone pairs of electron. Two lone pair of electron that oxygen is having. OH, OR. We have N groups, NH2, NHR, NR2. All these are having lone pair of electrons. Then we are having COO, COR, ester group. Then we are having acidamide group. They are also having lone pair. Correct? All these are having lone pair, right? Look at this group, thiol group, lone pairs are there, right? Then other than that, there are alkyl groups. It is having electron pumping effect. So it pumps electron to benzene. It also gives electron. How it gives? By hyperconjugation, it gives electron. We will see that in the upcoming videos, how it gives electron to benzene ring. It comes in ortho-para director, AR group, and halogen groups. Halogen groups, you know, Cl, F, Br, I, all this comes in ortho-para director. If these groups are present as primary substituents, then the incoming the incoming electrophile, it would enter at ortho and para position. It would be directed to ortho and para position with respect to the primary substituent. Now let us shift our focus on meta-directors. What are meta-directors? As I said, S group primary substituents that direct the incoming electrophile at meta position. Such primary substituents are referred to as meta directors. We have seen example earlier, COH, CHO. There are two conditions for meta director. S, primary substituent. What are those two conditions? Primary substituent should be positively charged. Just ulta of this. Okay. Primary substituent should be positively charged. Or primary substituent or the key atom is the atom that is linked directly to benzene ring. Okay, here the key atom is S. Now let me take the key atom as A. Okay, this is the key atom. The key atom should be linked to electronegative atom. The key atom should be linked to electronegative atom through multiple bonds. It can be double bond, it can be single bond. See, in this situation also X is electronegative, it would become negative and this would become positive. Right? So the key atom, either it should be directly it should be positive like this, or indirectly it can be positive like this. So there are only two requirements. Either the key atom should be positive, right? Or the key atom should be linked to electronegative atom through multiple bonds. Correct? In this case also key atom would become positive. So let us look at the examples of meta directors. Meta directors NR3 plus, right? Look at the positive charge, NH3 plus, NO2 plus, look, S double bond O, OH, sulfonic acid. Here also positive charge can come. When O minus takes electron, S becomes positive, right? So directly or indirectly it is, you are seeing that positive charge is being taken. C double bond O, OH. See how carbon can become positive if O takes electron. O is electronegative, it would take electron, O would become negative, carbon would become positive. So you are seeing how the key atom becomes positive here. That is the requirement for meta director. Look at aldehyde, look at ketone, everywhere carbon can become positive, right? Look at nitrile group, here also carbon can become positive. Look at this ester group, here also carbon can become positive. Look at amide group, see here also carbon can become positive. See here also there is ester group in ortho para director, here also there is ester group in meta director. The difference is the key atom which is attached to benzene ring. Here the key atom attached is oxygen. It can donate the pair of electron to benzene ring. Therefore, it is a ortho para director. Here the key atom, it cannot donate. It would become positive when oxygen takes electron. So here it is a meta director. So it only depends on the key atom which is attached. Look at the ester. Right, here the key atom attached is oxygen, therefore it is ortho para director. Here the key atom attached is carbon, which can become positive, therefore it is a meta director. Look at the other case here, amide. Both acid amide is there as ortho para director, here also it is as meta director. Difference is the key atom which is attached. Here nitrogen atom is attached, so it can donate a pair of electron, therefore here it can act as ortho para director. Here carbon atom is attached, so it can become positive when oxygen takes electron. Here it would act as a meta director. So it only depends upon what kind of key atoms are attached to benzene ring. In ester and acid amide case, it would depend solely on that. That's all about ortho para director and meta director. There is another category, there is another categorization, that is ring activator and ring deactivator. Let us understand that concept. Ring activators. What are ring activators? Primary substituents. Some primary substituent, they would make the benzene ring more reactive to electrophile attack, the reaction would take place very fast, right? Maybe 30 times faster than original benzene itself. So primary substituents that make the benzene ring more reactive towards electrophilic aromatic substitution are referred to as ring activators. What did I say? Primary substituents that make the benzene ring more reactive towards electrophilic aromatic substitution reaction are called as ring activators. Reaction would take place very fast. And just write here very slow and write here deactivators. Now you can make your own definition here. Now you can see primary substituents that make the benzene ring less reactive for electrophilic aromatic substitution than the benzene ring itself. That is the main thing. Than the benzene ring itself are called as ring deactivators. What did I say? Primary substituents that make the benzene ring less reactive to electrophilic aromatic substitution reaction than the benzene ring itself are called as ring deactivators. So if ring deactivators are attached, the benzene ring, it would become less reactive. It would become less reactive. Rate of reaction will be very slow compared to the benzene ring itself. Okay, and if ring activators are present, then benzene ring would be more reactive than the original benzene ring itself for electrophilic aromatic substitution. So what we have seen here is what we have seen here is all ring activators are ortho-para directors. Okay, except all ortho-para directors are ring activators except your halogens. Okay, so we will discuss this. Let us see ortho-para directors and how they are ring activators. Okay, we will prove that ortho-para directors are ring activators. Let us prove it. What did I mention to you? What are the two conditions of ortho-para directors? What is the eligibility to become an ortho-para director? Number one, it should have negative charge. Number two, if there is no negative charge, it should have lone pair of electron. In either of these cases, the benzene ring would get more electron. In either of the cases, if there is negative charge, it would give this negative charge, it would donate this negative charge, and this electron will interact with the 6 pi electrons of benzene ring. So electron density will increase in benzene ring. Electron density would increase. What is the requirement of ortho-para director? As I have said, it should either have a negative charge or it should have a lone pair of electron. If whatever the case may be, what would happen ultimately is that the electron density in benzene ring would increase, because they would not keep their electron with themselves. They would donate their electron to benzene ring. So ultimately the electron density of the benzene ring will increase, and that would make the electrophile more reactive to benzene ring. Correct? That would make this ring more reactive to electrophilic aromatic substitution, because now the electron density has increased. The electrophile will not sit here and will not stand, right? It would in a very fast manner it would go and attack the benzene ring. So ortho-para directors are actually ring activators because they increase the electron density in the benzene ring. And there is only one exception to it, that is halogen. Okay, why halogen is exception is because halogen is very electronegative. It's a very highly electronegative atom. Am I right? It's the highest electronegativity. So what it would do, it would give the lone pair of electron, but more than giving, it would take it would withdraw electron towards itself. That is, minus I effect will be very high for halogens. So more than what it gives, right? It would, of course, it would give the lone pair of electron, and that lone pair of electron would interact with the pi electron cloud of the benzene ring. But more than what it gives, it would try to take through inductive effect. So that is why, even though it is a orthopara director, it would act as ring deactivator, because the minus I effect of halogen is more. So that is the reason why halogen is a ring deactivator. Otherwise, all orthopara directors, they increase the electron density of benzene ring, and that would make the benzene ring more reactive towards electrophilic aromatic substitution reaction. Now, the second point is, all meta directors are ring deactivators. Let us look at this point. All meta directors are ring deactivators. Why? What is the requirement of a primary substituent to be a meta director? What did I mention? Either it should have a positive charge. That is the first point that I have mentioned, right? Either it should have a positive charge, or the key atom should be linked to electronegative atom through multiple bonds. Either it should have a positive charge, or the key atom, this is the key atom, the atom that is directly attached to carbon of the benzene ring. This atom should be directly linked to a halogen atom or a electronegative atom through multiple bond. In this case also, the halogen would take the electron and it would become positive. So overall, what we mean to say is that the atom attached to carbon of benzene ring, it should be positive, correct? So if it is positive, what would happen? It would try to withdraw the electrons of benzene ring towards itself. So that would decrease the electron density in benzene ring, right? If electron density in benzene ring is decreased, then do you think the electrophile would come eagerly? No. That is, the rate of electrophilic aromatic substitution would decrease, because now there is nothing to attract the electrophile, right? Much better was benzene compared to this, right? So compared to benzene, the electrophilic aromatic substitution, the rate, it would decrease, because it has withdrawn, the key atom has withdrawn the electron of the benzene ring, and the electron density in the benzene ring has drastically reduced. So this doesn't make the electrophile to be attracted to benzene ring. So that is why it would act as a ring deactivator. So the exception here is halogen atom, which is orthopara director, but still it is ring deactivator. We have explained why halogen atom is ring deactivator, because of inductive effect. So now let us classify, let us see the examples of activators and deactivators. Ring activators and ring deactivators. So whatever you have written for orthopara directors, you can write here in ring activators. Write this one, alkoxide, fine, NH2, NHR, NR2, correct? And then we have written about your ester, amides, everything that we have written there, thiol, everything that we have written there, you can write here as ring activator. All these are activating. Here I have not written halogen. So all of them are orthopara directors, right? Now in ring deactivators, you can subdivide them: meta director, right, and orthopara director. So orthopara director, which act as ring activator, you already know what are they? Halogens. So you can write here Cl, F, I, Br. All of them reduce the density of electron density of the benzene ring. And meta director, you can write all meta directors. You can write what were there, and NR3 plus, right? Whatever you have written there, NH3 plus, NO2 plus, acids, aldehydes, esters, nitrile, right? All of that which you have written in meta director, you can write it here. Also you can write your ester. The key atom here should be carbon, and acidamides, the key carbon should be carbon. Remember that. All of that which you have written, and orthopara directors also, here halogens you have to include in deactivators. Dear students, I hope you have understood the class on orthopara directors and activating and deactivating substituents. In part 2 of this video, we will see as to why the electron donators, electron donating groups act as orthopara director, act as ring activator, and why electron withdrawing groups act as meta director and as ring deactivator. If you have liked the class and if you have understood it, please do not forget to like, share and subscribe the channel. Thank you very much.